Okay, this is called a U-tube. Oh, it looks like U, right? Except it's a little bit squarish. So what I'm going to do is I'm going to put some water inside here. Oh, can you see? Water gets in like that. And if you look at this, the lever here is horizontal with the lever. Yeah? You think it's horizontal? Yeah, it is. It is horizontal. Like that. Okay. Maybe let's put it more this. So we say that water always finds its own level. It will always level out. Actually, all water that we have on the land when it rains will flow towards the sea. And the level of the sea water is usually lower than the land. It is. I suppose there is only one country where the land is lower than the sea water. Do you know which country is it? It's the country where there are a lot of what we call dikes, where they build walls to prevent the water from coming in. So that land is lower than the sea, but most countries will have the land higher than the sea.
Maldives.
Sorry?
Maldives.
Maldives?
Maldives.
No, the island. No, Maldives, yeah. Did you say Maldives?
Maldives.
Huh?
Maldives.
Maldives is not. Maldives is an island. So that island is higher than the sea. Okay? So when the rain comes, the water will flow towards the sea, because the water at the higher level will try to find its own level down to the sea. So if you look at this is called a manometer. A manometer is something just like this. Okay? Where is a U-tube. So these two levels are the same. Now what I'm going to do is I'm going to blow air into the left arm of the test tube. What do you think will happen if I blow?
The water level will
This right side will go up, and of course the left side will go down by the same amount, right? Huh? So I blow. Yeah. Okay. So you find that the left side has gone down this much, the right side has gone up the same amount. Especially if the two sides are of the same cross-sectional area, because water is not compressible. Okay? Water is not compressible, and therefore what goes down by that volume will go up by that volume. Okay? Now, which means that this side is open to the atmospheric pressure. Atmospheric pressure is pressing on the surface here. And then the pressure inside the closed section here is greater than the atmospheric pressure by this much. Okay? By this much of water level difference. Okay? Now if I let go, I let the air out again, then it will return back to its original level. Okay, now let me blow again. Wow, this time more. This time so much, and the one went up by so much. Okay, now why do you think that the pressure here has increased? Because I have introduced what? I've introduced more what?
More air.
More air. More air. Air means there are more molecules inside here. And you know what is happening? These molecules will hit on this surface with a greater force and push it down here. And it is greater than the atmospheric pressure by this much of water. Okay? So when the left arm from the camera is the right arm, right? If the right arm is lower than the left arm from the camera's perspective, it means that the lower level has a higher pressure, air pressure, than the higher level. Okay? So when I let it go again and let this air escape, it will return to its original level. Huh? Now what happens if I were to suck?
Go up.
This one will go up, right? Huh? Okay, so it went up by this much, and of course the one go down by that much. Okay? And now, if this level is higher than that level, that means that the atmospheric pressure, which is open here, is greater than the reduced pressure here by this amount of water. Okay? Why? Because I suck the air out of here so that the pressure here becomes reduced. Okay? So this is called a manometer. This is called a manometer. Now, usually a manometer is attached to something like this. It's attached to something like this. Okay? And this is a filter funnel. And this filter funnel, sometimes they use a teaser funnel. If I press this section, you find that if I press this section, this will go down. Okay? Let's see here. If I press this section, this will go down. So which means that if I compress the air here, if I compress it by pressing the rubber membrane here, this level will go down. Can you see? So when you compress air, the pressure will go up. So this pressure goes up, and this level will then come down, because it has got a greater pressure here than the atmospheric pressure by that amount of water difference. Okay? Now I'm going to immerse this inside here. I'm going to immerse this inside here and hold this horizontal. Now, what do you think will happen if I immerse this inside this jug of water? I will be going into a liquid right now. This part, you remember, if you go swimming, you go inside the swimming pool, how do you feel at your chest? You feel that the water will be pressing on you. So the pressure has increased. And water, which is not moving, will exert a pressure on your body. And that kind of pressure is known as hydro. Hydro means water. hydrostatic pressure. The water is not moving, so it's static, stationary. So hydrostatic pressure refers to pressure inside water which is not moving. Look, look at this level and that level. Can you see that this level is down and that level is up? Okay, so we are going to study the three factors of hydrostatic pressure. This one is not so accurate, but let's put this aside first. Let's put this aside, put it here, put it aside here. And then we want to study the hydrostatic pressure here. And the hydrostatic pressure has three factors. Three factors. The three factors are: one, we are going to study about the depth. That means the deeper you press this in, what will happen to the pressure pressing on that membrane here. Okay? And you will find that depth of a liquid is one factor. The next factor is the direction. If you turn the direction different ways, how would the pressure, the hydrostatic pressure, vary? And finally, we have density, depth, direction, and density. 3Ds. Depth, direction, density. So if it's density, we must keep the other two factors constant. If we study one factor, the other two factors must be constant. Okay? So now we look at this factor here, which is depth. Okay? So this depth is what? H1. Okay? This depth is H1, and therefore the pressure here, P1 will be atmospheric pressure plus what? A1. Okay? So we have here the pressure at H1, which we label as P1, is equals to atmospheric pressure plus the difference in the level A1. Okay? Alright. Now this is your book. Let me take my book so that you can have a look at it. Okay. Now we have we immerse the teaser funnel deeper. What page is that? Page 49. We immerse the teaser funnel deeper, and then we immerse the teaser funnel to H2. Is it H2? So what is the pressure at the bottom there? P2. P2 will be equals to the atmospheric pressure plus A2, small a 2. Okay? So we can say from here, in quantitative terms, that the deeper you go inside a stationary fluid, the greater will be the pressure. Okay? And that is shown by, turn over to the next page, by a can like that. One page only. Okay, by a can like this. So this can has got three outlets at A, capital B, and capital C. A is at A1, H1, so pressure there is P1. B is at H2, pressure there is P2. And C, outlet, is at depth H3, so pressure there is A3. And there you will find that because the pressure at C is greater than A, the water will gush out to a greater distance. I mean, if you look at this is common sense, you know. So this is the first factors we study. And the second factor is in figure 6.5. 6.5, here we turn the teaser funnel in different direction but at the same depth H1, okay, or same depth at H, okay, same depth at H. So it's the same depth at H. First is facing downwards, secondly is facing sideways, and we find that if it is the same level H is facing downwards and facing sideways, the water difference A is the same, and meaning that the pressure here at P1 is equal. Okay? So it's irrespective of direction. So the pressure, if you go inside the swimming pool, whether you are downwards or upwards or lying sideways, the pressure on you will be the same. Okay? Because you are the same depth. And therefore we have this special flask in figure 6.4, where we drill holes at the same depth all around the flask and fill it up with water, and then you press down on the plunger. And when you press down on the plunger, because they are at the same depth, the pressure is the same, so the water will gush out from the hole with equal force. Okay, so that shows that the pressure at the same depth will be equal. And finally, we have in figure 6.7, where the figure on the left of 6.7 is at the lower density than the figure on the right. So if this is at the lower density, you find that small a1 is smaller than a2 over on the right, and therefore we say that the denser the liquid, the greater is the pressure exerted by the liquid. I think it's common sense. Later on, should we play with mercury, we want to put our hands inside mercury and feel that the pressure on our finger will be very great, because mercury is very dense. It's about 13-14 times as dense as water. Okay, so density, if you have got a greater density liquid, you will feel a greater pressure at the same depth. Okay, yeah. So now we find that there are three factors that the pressure inside a liquid depends on. Two of them will increase as they increase, but one of them is independent and it will not affect pressure, and that is direction. But when you go inside a liquid which is denser, you will find that you will feel a greater pressure. And then by our common day experience, when you go inside and dive inside water, the deeper you go, the greater is the pressure on your body. Okay, so there you are. The two main factors that increases pressure inside liquid is density and depth. That's all. Density and depth. Okay, now we will do the theory.